This is section 1.5, composition of functions, and three things that we'll be covering in this unit is how we create a new function by combining it or composing it with another function. And then we're going to evaluate a composition of functions, and then we're sort of going to go in reverse where we decompose a composition into two separate functions. All right, so here's an example of a composition of functions. So if we have a garden, let's say it's a circular garden, and we have a radius of 15 feet, and it's going to be covered with topsoil, and the topsoil is $1.25 per square foot. Okay, so if we think about it, we can calculate what is the area of this garden. We're only told right here that the radius of the garden is 15 feet. So we need to find out the area of it. So we know that area, if we input radius, okay, pi r squared is equal to area. So if I input radius, I get an output of area. All right. Then if I want to figure out how much it costs, well, then I'm going to take that area and I'm going to input it into my cost function. All right, the cost function says that for each square foot, I spend or I have to pay $1.25. That gives me my cost. So I take my input of my radius, my output is area. That area then becomes input to my cost function, and then my output is cost. Okay, so if I want to figure out the area of the garden to the nearest square foot first, kind of do it in two pieces. My radius is equal to 15 feet. So my area is a function of radius equals pi r squared. I'm going to input 15 for my radius. Area at 15 feet is pi times 15 squared. All right, so that gives me the area of my garden, and that it says to the nearest square foot, so that equals 707 feet square. So then it says use the answer from part A. Okay, this is equals area to calculate the cost of covering the garden with topsoil. So cost is a function of area, meaning I input area and I get an output of cost. And cost is represented by $1.25 per square foot. And so I'm going to take that 707, and that gives me an output of $883.75. So that's what a composition of function is. We're really combining or composing two functions together. We take one function, the output of this function now becomes the input to my cost function, and then I get a final output. So here's sort of the formal definition of composition of functions. And just like I said before, so when the output of one function is used as the input of another function, we say that the entire operation is a composition of functions. You can see it in two different notations. This says f. The signal notation there is of g of x. Okay, so f of g of x, we can also write it this way here, where the inside function is g, and then the outside function is f. Okay, and it's sometimes easier to think of it in terms of what my inside function is and my outside function is. We always work from the inside out. Okay, so if I evaluate my inside function at whatever this input is, and then once I evaluate that, that becomes the input to my outside function. This will make more sense when we do an example. All right, so let's look at this example here. It says that we have some function b of t is bushels, the number of bushels of apples produced by t trees. So if I say b of t, okay, equals b. So if I input the number of trees, my output is how many bushels I get from those trees. Okay, and then it says let P of B be the profit that we can make on bushels of apples. So if I take that B, that output is the number of bushels, I input it into this profit function. My output is the profit I make from B, which is bushels of apples. So let's look at these two choices here to see which one makes sense. So it says which one has meaning. So if I look at the first one and if I say the profit from 10 bushels is then input into my bushel function, that doesn't really make sense. That green would have to be the number of trees. So that really doesn't make sense. I don't input profit into my bushel function. I input t. Let's look at the other function. This one says the bushels of apples I get from 10 trees would then be input into my profit function. That one makes sense. So if I say that in words, I'd say profit I make from the number of bushels from 10 trees is equal to P of B of 10 equals that. Okay, so this is the number of bushels I get that I harvest from 10 trees. All right, so then I input it, number of bushels from 10 trees. And then when I evaluate that, I get that profit from 10 trees. All right. So we can also evaluate composition of functions when we look at tables. So this table here, my input is x. My output is f of x. Here my input is x. My output is g of x. When we do composition of functions, we always start from the inside out. I'm just going to do a couple of these. So this one says evaluate my function f when my input is 7. Here's my function f. I want to see when my input is 7, my output is 6. Okay, so I can say that f of 7 is equal to 6. I'm going to take that and I'm going to input it now into my outside function, my g function. So now I'm going to say g of 6. Okay, so again, I input 7, I output 6. That output then becomes the input to my g function. So now I'm going to look, where's my g function? Here's my g function. If I input 6, I get an output of 10. Okay, so this is equal to 10. All right, let's look at another couple here. So this one underneath here says, I'm going to look at my g function and I'm going to evaluate it when my input is equal to 2. So I'm going to go to my g function, right? G of 2. Here's 2, my input. I get an output of 3. So I evaluated g of 2 is equal to 3. I input 2. I output 3. I'm going to take that output and now it's going to become the input to my f function. So now I'm going to have f of 3. Okay, now it becomes the input to my f function. Let's look at my f function. f of 3. Okay, I input 3, I output 7. So f of 3 is equal to 7. And then let's look at the last one here. I can apply a composition of functions to the same function multiple times. So my inside function here, I'm going to evaluate f of 3 here. All right, so when I do that, when I read the table, f of 3 is equal to, right here again, I input 3, I output 7. I'm going to take that output and I'm going to put it back into my f function. That's my outside function. So f of 7 now is, I input 7 into my f function, I get an output of 6. And that's my final answer there. Okay. We can also do the same process by reading graphs. So we just looked at tables. We can evaluate algebraically, and we can look at graphs. So again, we're always going to start from the inside out. All right, so I have function k and m. Let's just see where those are. Here's my k function, and this one is my m function. All right, so we're just going to read off the graphs. So this first one says the inside function is evaluate first k at 1. So if I input 1, I go up to the graph. Okay, I input 1, my output is 2, right? Input 1, output 2. So k of 1 is equal to 2. Now I'm going to take that and I'm going to input it into my outside function, my m function. So this is my outside function. So I'm now going to have m of 2, right? I took that output, it becomes my input to my m function. I'm going to read my m function. Here's 2, my input. My output is 2, negative 1. Okay, so when I input 2, I output negative 1. All right, we can go reverse. We can start with the m function, m of 0. I'm going to evaluate that first. Now m is my inside function. So I want to look at my input 0. Here's my 0. What's my output? I'm going to read my graph all the way up here. When I input 0, my output is 3. So m of 0 is equal to 3. I'm going to take that output now, and that becomes input to my k function. All right, so now I'm going to go to my k function was here. I look at k of 3. Here's my input of 3. I'm going to go down. I read the graph. When I input 3, I output negative 2 equals negative 2. Okay? All right. So now let's algebraically look at some composition of functions. And I have 3 functions here. I have a function f of p, g of q, h of x. And again, we're always going to start with the inside first. So first I want to evaluate g of 2. So what's my g function? It's right here. So g of 2 is equal to 3 times 2 plus 1 is equal to 7. Okay, so I input 2. My output is 7. Okay, I'm going to take that output now. All right, so because g of 2 equals 7, this can become f of 7. I take that output and I input it into my f function. Here's my f function here. F of 7 is equal to 2 times 7 minus 7 squared. And that is equal to 14. 15 minus 49. I didn't do the math. Okay. All right, let's look at the next example. All right, so I don't always have to evaluate with numbers, right? When we were using the difference quotient, I didn't always have an input of a number. And in this case, I have g at t. So I'm inputting some variable t to my g function, which is here. So g of t just means I'm inputting t. So that's equal to 3 times t plus 1. Okay. And now this whole expression here now becomes my input to my outside function, my f function. So this becomes input f of 3t plus 1. Okay, here's my f function. So everywhere I have a p, I'm going to put a 3t plus 1. So this equals 2 times 3t plus 1 minus 3t plus 1 squared. Let me expand this out. Okay, I'm going to distribute that 2 inside the parentheses. So that becomes f of 3t plus 1 is equal to 6t plus 2. All right, I'm going to distribute that, not yet, minus. I'm going to expand this out. This is 3t plus 1 squared, so that's 3t plus 1 times 3t plus 1. If I do FOIL, I get 9t squared plus 3t plus 3t, and then my last term is plus 1. These are like terms. This becomes 9t squared plus 6t plus 1. Okay, so I have this negative sign on the outside. I need to distribute that. All right, so this becomes 6t plus 2. I'm going to distribute that negative sign, minus 9t squared minus 6t minus 1. Okay, so now we have some terms that will simplify out. I'm going to just write this. Okay, I have a negative 6t and a plus 6t. That reduces out. I have a minus 1 and a plus 2. That becomes 1. This equals negative 9t squared plus 1. Okay. I'm going to leave that other one for you guys to do. Let's do one more here. We're going to evaluate f of g of p. I'll let you guys do this one on your own. My g function is right here. G of p is equal to 1 over p squared plus 1. So if I take that as what g of p is equivalent to, so I'm going to take f of g of p, which is 1 over p squared plus 1. Okay, and my f of p function is this function right here. So that becomes the square root of 1 over p squared plus 1. So I'm just taking, everywhere I see a p, I'm going to put 1 over p squared plus 1. I could simplify this a little to be the square root of 1 over square root of p squared plus 1. Okay, if I take the square root of 1, that's just 1 divided by p squared plus 1. Okay, if you do this other one, we don't always get back the same result if we do the opposite. So this one has f of p as my inside function, g of p, g of f of p. We don't always get the same thing if we go forward and back. So that's something to watch out for. Okay, so another topic is decomposing a composite function. So we just composed functions previously, what if we want to undo or decompose them? Okay. And sometimes in calculus a lot, we will do composition of functions. But really, when we decompose a function, we're just writing it as the two simpler functions that we had combined. So we're undoing the combination. So if I consider this function here, h of x is equal to x plus 10 raised to the 5th power. All right. So a lot of times when you see parentheses, that's sort of a clue. I have this thing inside the parentheses. All right. So this is actually something that I would call my inside function. And then that whole thing is raised to the 5th power. Okay. All thing raised to the 5th power. So if you think about it, it kind of might remind you of if I just said x to the 5th. Instead of x to the 5th, I have x plus 10 to the 5th. All right. So we could think of this outer part, whatever this is raised to the 5th power, as being my outer function, and that my inner function is this thing x plus 10. So again, if I let my outer function be equal to f of x equals x to the 5th, and if I let my inner function be equal to x to the 10th, I could rewrite this function h of x as f of g of x. So g of x is on the inside, f of x is on the outside. Okay, so if g of x is equal to x plus 10 and f of x is equal to x to the 5th, f of g of x would be equal to, here's my g of x, would be f of x plus 10, which would be equal to x plus 10 to the 5th power. So let's look at this. This is a similar example. If I were to try to decompose this function, again, one thing that you want to look for when you're looking for, when you're trying to decompose a function is trying to figure out, is there an outside function and an inside function? And a lot of times if there's parentheses, that sort of gives you a clue. This would be my outside function. My inside function would be the thing inside the parentheses. Okay, so if I were to decompose it so that I had this h of x function is my inside function, and then my outside function f, I could rewrite that to say g of x, my inside function, is equal to x plus 5. And then I could say my outside function, f of x, is equal to x cubed. We can try it to evaluate that out. If g of x is x plus 5, f of x plus 5 is equal to, if this is f of x, everywhere I see an x, I'm going to put an x plus 5 cubed. So that works out. Another way that you can identify a composition of functions is if you have an exponent. Okay, so even though there's not parentheses around here, this is really 2 raised to some power. Okay, and if I write that exponent in parentheses, that's sort of a clue that that's my inside function. All right. 2 raised to some power x would be my outside function, and instead of x, I'm raising it to this inside function. So again, this exponent would be my g of x. So g of x is equal to x squared plus 5. F of x would be equal to 2 raised to the x power. If I compose it, I would say g of x is equal to this here, x squared plus 5. So f of x squared plus 5, if f of x equals this, is equal to 2 raised to the x squared plus 5. And my last example here is that when you have something under a radical sign, the thing under the radical sign most often is the inside function. So we would say that g of x is equal to x squared plus 5. I would say f of x is equal to this whole outside part here, cube root minus 2. So that would be 4 times the cube root of x minus 2. Let's put it together. If I evaluate my inside function, g of x is equal to this term here. So f of x squared plus 5 is equal to, everywhere I see an x, I'm going to put an x squared plus 5. So that's 4 cube root x squared plus 5 minus 2, which is exactly what I have there. And that's it.